Yes. Now, so maybe then I can give the word to Toby again, because because we need some final channel for the discussion here again.
Okay.
Good. You know, stay here because there's a lot of course.
I don't know, you mentioned it, so if does it make sense to develop others in the X direction when you don't have a really big job? Or will
I mean, it's
will
always
lose so much gas efficiency?
Yeah, I think there's only a few machines where it is actually disadvantaged parallelizing also in the X direction. So those are the machines that have an architecture which is such that that you cannot directly communicate to somebody else except through a central hub. As you remember, in the machine in Ulm, we had the situation that the processes were arranged in such a way that there were 24 processes on each hub. It's a rather small number, of course, 24, and then you have all these different hubs here. And all these different hubs, they were connected through a super hub.
And those hubs were really switches.
What? These are switches, yes. So that means if you wanted to communicate from any of these 24 and here to here, of course, you would stay inside this hub. If you wanted to communicate through here, of course, you have to go outside. But you have to compete against everybody else who also needs to go outside and back inside again. And so that produces a bottleneck very easily, even though this line may already be 10 times faster than this line. Which was indeed the case, but it was only 10 times faster and was not, for example, 30 times faster. And so we were easily actually reaching this bottleneck. And so this is an arrangement which we had back in Odense. This was a cluster administered by chemists. Another layout, of course, is one where you have all these processes on a mesh. But again, these were normally two-dimensional meshes. They are not three-dimensional meshes. So I think this is an issue that we have to keep in mind, of course. So back then, it was clearly not equivalent to having, for example, 8 times 64 processors, or 16, or 16 times 8. It was better to have, this one was better, and this one was worse. And it turned out that it was even better to actually have only 4 times 32. It was ridiculous, of course. Because the smallest surface to volume, of course, you have, if these two numbers are approximately comparable. And yet this one was at least 3 times faster than this, on this type of cluster, which is not, unfortunately, so common anymore. Now, if you go to the new generation of machines with 800 to 12,000 processors, I think there's no word really of how exactly the layout will look like. And so certainly it's very important to experiment with these different layouts, and hopefully we'll be back to such a situation. And then, of course, it becomes clear that it's likely that if you run on 100,000 to 10,000, it would be already. I mean, you would think that this is maybe not as good as having, for example, 10 times 100, for example, right? That looks much more natural than just having one in this direction. So I think it will be a major improvement if we have this luxury in terms of surface to volume area. Right, what else? So we have the...
Okay, so...
Maybe we can wrap up on the manual. Did you decide on
again the menu.
Did you decide on
Yeah, I think a little bit, right? I mean, my recollection is we wanted to say there should be an additional section about leading the leader to the different subroutines.
and creating your own run from scratch.
Yes, yes. That was one of the things we discussed on the way to lunch, of course. I mean, creating your own run from scratch is in fact not so easy. I mean, because you don't even know what you really want.
What would, I mean,
And so this process of developing exactly your idea of what you really want and what you then should set up, they go a little bit hand in hand. One has an effect on the other.
right, but I think if we have a tutorial and that starts with, let's set up a one-dimensional subway and have it propagate through the box. That would be great.
With or without boundaries?
About, maybe.
Then you want to visualize it, of course, right?
Which you can actually do with blue paper. Right. So, what about the multi-author paper then? That requires lots of discussion.
Yeah, we had discussions of this, maybe actually the first time really only during the last pencil code user meeting. And there wasn't really much development after that anymore. Except that a few times, so it was Anders and Jeff Roishi from New York, and a few others who have discussed this at special occasions. And there is one beginning of a draft. It's actually more or less empty subsections on the way. Maybe we should highlight this briefly.
Maybe, yeah.
Yes, so I'll just do here first view on tech pencil code paper.ps. That's it. You make it bigger. So you see many authors, but many other authors are not yet included. Right? What?
Sven is the first person.
Yeah. It's alphabetic, yes. I think, actually, by the way, it was, at times it was of a major concern for Wolfgang and myself to make sure that nobody understands the pencil code as somehow being our product, because obviously many of you have contributed to this. And especially Anders has contributed a lot of things. It's just that Wolfgang and I have initiated this whole thing. So it would somehow be wrong, I think, if people actually understand this to be something which should really go to our credit all the time. That would not be right. And instead it should be just a platform which people can use to implement their own things if they feel it is something useful to share with the open, bigger community. So, so therefore, I think it's extremely important that both Wolfgang and I are not at least either prominently first or last authors, of course. That's on my level. Anyway, so so I can do it either forwardly, alphabetically, or backward alphabetically. In both cases are fine, of course. So, for example, in the pencil code manual, you will see some listings where it was inversely alphabetically, by the way. Here the style is a code description. Right. And then we have, so then we were basically thinking of items that should include, or may include, some of the test or sample results. But not exclusively. There may be additional, not every pencil test, of course, is versed by a publication entry. And vice versa, there may be things which are not versed as a test, as a sample, because they wouldn't sample anything new yet anymore, but they would otherwise be a good test. So these are ordered in such a way that they start, that may be not the wisest, of course, they start from zero-dimensional problems, going to one-dimensional problems up here, one-dimensional problems, to of course, two-dimensional problems and then three-dimensional problems. People were always wondering, what does it mean, zero-dimensional? Zero-dimensional means nothing? No, it does, of course, and it's if everything happens at the same point. And so one particular application is heating and cooling. If you have, and that of course may be non-trivial. If you have a cooling function that depends, for example, on the temperature, the time function, the time profile with which something will cool at one point, of course, is non-trivial. And so that's an important first test, of course. Anyway, so here you can read through this. Yes?
But that's still, as a first, that's a strange test to start with, I think.
Maybe. Yes, and so I was also not too sure whether this orientation of structuring actually makes much sense. I mean, in some sense you may think it's natural, a second thought is completely unnatural, and the third thought is maybe more natural than one thought at first. So I haven't
But
So you are in the middle now, in the second stage.
But I mean, if I read the paper and then look at section 3.1 and think maybe I don't really want to, maybe this code does something completely different than what I want to do.
Maybe it doesn't do more than 0
I
I
mean,
mean,
So maybe we should start with order the test and on how common they are.
Meaning what?
Well, meaning, I guess this sort of shock tube test is, I mean, what people
Yes.
usually do.
Okay, shock tube test is indeed an important thing, of course.
It's also the first thing people will say about the difficult that they can't have in shock.
Yeah, no,
So shock tube test. I think shock tube test and something with the avium is so really convince people that this is not a big crap.
And we should also order the things maybe a bit how good the pencil code performs. So maybe we should start with the simple test that works extremely well. And then
Wait, this is of course on the web page actually. There's actually some tests already, as you know. So if you go to the pencil tests here, so that's actually, you've hopefully all seen that, right? So then you can ask the question, is something wrong with this test? Yeah. I mean, that's sharp enough jump, right? And then there's this interesting paper.
what's with shock viscosity?
No, that's with uniform, constant. Shock viscosity is something extra. There was in this test here by, here, this one, by Sam Ford from University of Leeds. The refraction shock errors and low order accuracy of Zeus. You know that paper? So they attack the Zeus code, of course. Can you actually get it online?
Yeah.
Click on the run page in robot alert. Okay. Yeah, even though it's not even 100, but that's about 100 kilobytes, right?
No, actually it's really slow.
Okay, so here's this paper, and then let's look at the plots here they have. So they know that there's this sharpening factor. No, there's afterwards. So here it's actually that. Here, put this plot in. So here you see the correct solution, which is this linear line here. It's the correct solution. And then with Stemford's upwind scheme, he gets the plus signs. And I have very much online. And then you have the Zeus code. The Zeus code has implemented sharpeners. So of course, if you think this is not very sharp, the sharpener will say, all right, let's make it sharp. And so then that's in their language the result from the Zeus test. Looks of course very different, but if there's such a tool invoked with a sharpener, you can actually turn it off, of course. We see. Oh, actually I'm wrong here. This is with the correct parameter here. This is Qlin. Does anybody know the Zeus code to any extent here? So there's this free parameter which you better know that you should put it to 0.25 and not over to 0. So then, and then some false test comes on the next page, I suppose. Right. So that's some false results, this one. And then we can keep that picture and go back to our web page. Sorry, our page was here. This one maybe. No. There's the web page. Maybe it's the first one then.
Yeah.
And one more time. Yes. So, and then you can highlight this plot, and you click on this plot, then it becomes bigger. So here you see how well our code does, for example. So that's certainly better than some false result, which you would say is not surprising. I mean, ours is a 6-order code as opposed to lower code. So that code is doing easily better than that. So it's not right to say it's not good at charts. Yes. Depends on where free, So anyway, so that's yes. So you're saying you should do shock tests first.
Yeah, or it's also
Another important test, of course, is which I like and which was part of the original draft, is total energy conservation. I mentioned this in once. So we have a sound wave which propagates in this direction. Of course, it piles up, develops a shock then, and then it will, of course, decrease in amplitude. So that means that the kinetic energy will decay. That's Akin. Of course, this must turn into heat, so the whole system will become hotter. And then you add these two functions together and you get a flat line. So the total energy is conserved by the code. So people always say, okay, our code is not conservative. By saying it's not conservative, it means it's not conservative to machine accuracy. So that means if you see any departures, and the departures of the order 10 to the minus 4, these are departures through the discretization error. The scheme itself has an error, but it's not forced by some technique to be accurate to the machine accuracy, to the last digit. So that means if you see any departure in such a plot, you can then use this as an indication of saying if there's a departure of 10 to the minus 4, then you cannot trust anything more accurate than 10 to the minus 4 here, obviously. If it's only 10 to the minus 2, you cannot trust more than that. So that gives you then a very easy tool to assess the accuracy of the scheme. On the other hand, if you have perfect conservation of mass and momentum, and you run on only 8 mesh points, you may be fooled into thinking that everything is very accurate because, of course, it's accurate to machine accuracy. But then there may be details in the solution, of course, which are not accurate because there's no guarantee that anything else will be accurate to machine accuracy. Certainly not, of course. So that's simply important to realize. So our code, of course, does conserve energy, but only within those limits, which even here you don't see.
But you could do it here with a magnetosonic wave also. And,
Yes, and that I have.
I think that would be interesting.
Yes, I can show you. Should I show you?
yeah.
Because I have it even, I don't even need to recompile this, but so there's it's under runs, under 1D tests, and that's called sound adiabatic magnetic. So I did this on the 12th. And the data, of course, there, so I can just plot them. Maybe there's something running in the background still. No. Okay, so here what do you see in this plot? You see big enough. So you see that the kinetic energy decays and the magnetic energy decays. These are the white and the red lines. Then you see that the temperature increases. So the temperature increases, again, the white line up here, so it increases, becomes hotter. It also becomes cooler. This is, of course, because of adiabatic expansion again. Then it can become cooler again. So, and then, if you add kinetic energy and thermal energy together, that also still increases. And that's the time when Zeus people certainly will say this cannot happen. Because in Zeus, of course, energy conservation means really that all the energy is conserved except magnetic energy. That's because treating magnetic energy also fully conservative is not really easy. So all the rest, why this actually still increases, is because of ohmic heating. That's why if you iron your shirt, it becomes hot. I mean, So that's resistor feeding. That's what makes this line here increase. And if you then add this together with that, and together with the thermal energy, you get this flat line here. This flat to not machine accuracy, but flat to long errors. So I like this, and of course the first time you do this, and especially if you put in, for example, dimensions. But somebody wanted to have a CP. In many of our calculations, CP is always 1. It's like saying people in relativity, they always have h bar equals 1 and c equals 1, of course. We can do this, by the way. If you want, if you can run the code with h bar equals to unity. But normally our CP, the gas constant, is equal to unity, and so somebody wanted it to be a 2.5. And so he implemented this and thought everything was alright, published the paper. And actually, the first time I checked them, a few years later, because I didn't really care too much about this, I found this, all of a sudden the energy conservation is no longer working correctly. So it's such a simple test to test at least a few critical aspects. And so changing whether once you have to put dimensions into play, whether that still is okay, of course, when you have implemented everything correctly, it's easily tested through testing the conservation. So that is nice to use conservation as a test rather than as a constraint of satisfactory machine. Does it mean that we want also non-linear sonic base? Now, the reason why the whole thing should be multi-author is, of course, because there are so many physics aspects that are tested and implemented by a number of different other people. And so we should, of course, head also come towards these additional tools.
I think it would be good to start with these very general things that would also illustrate the inverted scheme.
Yes. What about advection test? I think they are important for describing a scheme.
Yeah, because that would show that there's not so much amplitude.
Amplitude and phase error.
Yeah. And that also shows why we need this sort of thing.
Yes. So that would actually, in which sequence do you want to do that?
Maybe first.
So now we go back to do something boring first to give the impression that it more or less can do advection.
So you want advection rather than nothing first?
No, but according to that logic, I mean,
yes.
It seems natural to build things up, be it in terms of physics, be it in terms of dimensionality. This is more like building things up in terms of physics, which is natural which is more natural than dimensionality, because sometimes you do similar stuff in 2D or 3D, and there's no point in discussing it in different places. So advection tests are physically about as minimal as it can get, because there's no physics, just kinematics. And then, so
And such things would be going under which heading then, if you no longer take one-dimensional tests? It would be going under what heading?
I mean, except for the if we put the zero-dimensional stuff before that, this is all one-dimensional, so it's still.
So we what do you think?
No, we can start like this. Just forget about the zero-dimensional.
Okay.
You mean not do that at all, or
No, we'll put them in
So
here.
then we actually have that so far though already. Okay, let's just continue without thinking of this. Then what do we do next?
Maybe the test which are not so physically interesting can be put in an appendix.
Yes.
Okay.
Oh, by the way, the possible place where the source should be published, I was thinking, could be the update supplement, because that is where also the use code has been documented in three papers in 92. Anyway, so that's a supplement already, so there's no constraint on the length really. So if it disrupts the flow of the paper by putting into the appendix, then we can as well leave it in the main part of the paper because the paper can be long. The understands the protocol in front of him.
Of course. I just wanted to see which journal they were in. So this is Java. I thought there was a reference paper for the protocol. I just wanted to know which. I thought that was ANA.
Okay.
At least the acknowledgements are already in there. That's good.
They are.
Don't have to worry about them anymore.
So, can you maybe, yes, that's a better page, of course.
Okay, you meant, shall there be anything in the above test?
In the what test?
Shall there be anything in the paper except, I mean, other than test?
Other than tests.
Oh, there's code description.
Code description, yes. Yes. Code description and tests. I think that's really it, I know. What else? By the way, another reason why such a paper would be useful, I think, could also be that often you come across simple textbook problems. One of them is, for example, the MRI instability. Another one is the genes instability or even thermal instability. You learn about this in textbooks, and with some abstract thinking you can understand why certain graphical illustrations even make sense. And that's as far as it gets. Instead, having, of course, things really live in front of your eyes, in terms of an animation or something that you yourself have actually set up, could be a major enhancement. So one could actually think of some of these experiments as being illustrative of the physics and also illustrative of the simplicity with which they can be implemented into the pencil code. So I could actually sit down here for 5-10 minutes and just completely from scratch implement any of these instabilities, hopefully. I mean, saying such a thing may not actually turn out to work in 10 minutes, but then certainly 45 minutes should be okay. I mean, because it works correctly after 5 minutes, and after 10 minutes you realize it's actually not quite right, and then it takes another half an hour to make it work correctly, and another final 5 minutes to save the plot and pick it up from the picture or something. So, so that's maybe true with these examples here, that they are good illustrative physics problems.
Also showed the code as being diversified.
Yes.
I think it's a good message also to say.
Yes, indeed, these three things, MRI instability, it's a bit small project, some of you perhaps. MRI and thermal all illustrate, first of all, they have in common that we are talking about instability. So that means there's a common background in terms of the existence of a dispersion relation, which we have for all three problems. You can plot the dispersion relation and see whether it pops in at large or small wave numbers. And in fact, all the plots are rather similar, actually, in some sense. And that's as far as textbook stuff is concerned. And then you actually run the same thing. You can verify that the stuff grows with the growth rate, which is exactly equal to the imaginary part of the growth rate. And you see the functional form, which is the eigenfunction. And then you see when it saturates, it becomes non-linearly derived.